this is called a sub-lattice of the previous lattice. So it's a lattice, but it does not cover all the points which were in a previous lattice. So it is a sub-lattice. Again, a usual mathematical term, groups, subgroups. Okay, so things like that. So here is another example. So this is a two-dimensional lattice, but I have only one basis vector, so I can cover only much smaller vectors. And here in this case, the basis vector is only one. So it is also a sub-lattice, but it is not even full rank. Earlier at least it was full rank, now it is not even full rank. So it's a two-dimensional lattice, but only one basis vector. So I am covering only some small part of it, only straight line. And there are some non-examples also. Like if I look at all integers z and I look at this 2z plus 1, they don't form a lattice because although they are discrete, they are not a subgroup. I mean, because x minus y don't belong to this. So I have an integer 2x plus 1, I have an integer 2y plus 1. When I subtract them, I get 2 times x minus y, which is even, whereas these were odd. So it is not even of the form 2z plus 1. So it's not even a subgroup. Rational numbers don't form a lattice because they are not discrete. They are infinite in any interval. This one 1 comma root 2, so all combinations of 1 plus root 2, x plus root 2 y, they are also not a lattice because they are not discrete. So there are many examples of this kind. And then I can talk about how I can interpret basis in terms of a vector. So in terms of a matrix. So look at the lattice. Lattice was linear combinations of bi. So I can take these bi's as column vectors and then I can multiply by a column vector. For example, I have a column vector here. Okay, here. I multiply this b with some vector z. Okay, column vector z. And in the column vector z, I write 1 followed by 0, 0, 0, 0, 0. That means I am taking the first column 1 time, next column 0 times, next column 0 times, next column 0 times. So it is the linear combination which is created by 1 comma 0, 0, 0, 0. If I had the column vector z as 1, 1, 1, 1, 1, 1, it would have meant b1 plus b2 plus b3. So this is exactly what we are trying to say here, that if I have a basis vector matrix, that matrix can be multiplied by a vector z and I will have a lattice. Fine, everybody is okay? So do I need to give a break somewhere in between? Yes. Yeah. This is very high mathematics. I have reached only 44 slides, I have 134. Okay?
This one.
Yeah, sure. about what 500 bits. So 512 bits का होगा ये, ठीक है. This is elliptic curve of 512 bits. Okay. So this is elliptic. combination of basis vectors. Okay, and this idea was that you have a basis vector matrix, you multiply it by a set of integers and a column vector of integers, and you get one lattice point. And by varying that column vector, you can get all lattice points. Okay. Now, there is something which I don't need to bother right now. There is a fundamental parallelepiped, which is the parallelepiped created by these basis vectors, linear combination of these basis vectors, where the linear combinations are now real numbers between 0 to 1. So what do I mean by this? Let's look at this lattice. There is a basis vector b1, there is a basis vector b2. Their integer combinations are going to give me this entire basis. Now when I say parallelepiped, I will take the first basis vector multiplied by a number between 0 and 1. I will take the second basis vector multiplied by a number between 0 and 1, and I sum the two. So I am going to cover this area, this green area. This is called the parallelepiped. So if you can now imagine 3 dimension, 4 dimension, n dimension. So this combination of these basis vectors, the smallest that unit, will be the parallelepiped. And there are certain results on the volume of this parallelepiped which are of relevance to cryptography. So this is another basis vector, and this is the parallelepiped. So you can understand what is the parallelepiped in terms of these basis vectors. Okay. This third one, this is also a parallelepiped. One very important result that we know is if the parallelepiped contains another basis vector, another lattice vector, like in this example. Here you see this parallelepiped does not have any lattice point. Here also you don't have any lattice point within the parallelepiped, but here you have a basis vector within the parallelepiped. The moment you have it, it is not a lattice. Okay. So this is a very simple result which we can understand geometrically. This is not a lattice. Okay. So this B1 and B2, they are not the basis. Okay. This could be lattice, but B1 and B2 are not the basis. Okay. So then essentially this is what I have said here in this very famous theorem. That is, if I have n-dimensional lattice and the basis vectors b1, b2, b3, bn are there, which are linearly independent basis vectors, then the parallelepiped formed by these basis vectors and the lattice point have nothing in common. So the intersection between the parallelepiped and the lattice points is null. Okay. Except 0, there should not be anything. Right? So 0 is the only thing which is permitted, which is this one. Nothing else should be there. Okay. Now, if I give you a bad basis vector, like in some case, like I gave you very bad basis vector, which are not orthogonal. Orthogonal are very nice, like this one. They are very nice. Using their combinations, I can actually create in a structured manner the entire lattice point. But here, the lattice vectors are not very nice. They are not orthogonal. Many algorithms work very well if the lattice basis vectors are orthogonal. So there is a need to make the basis vectors as orthogonal, and hence we sometimes need, can we make orthogonal vectors out of not orthogonal vectors. And this is the famous Gram-Schmidt orthogonalization, which you may have already studied in some course. So the idea is very simple. I have this basis vector b1 and this basis vector b2. So what I will do, from b2, I will drop a projection on b1, and I will subtract that. So I will now get this b2 dash, this one, green color. Okay. So this b2 dash is nothing but I subtract this projection of b2 on b1 and subtract from b2. So you look at this picture here. From b2 I drop a perpendicular here. So I will have this triangle. Okay. And in this triangle, this part I will remove. So this minus this, and I will get this vector, which is what this is. So if I have two vectors which are not perpendicular, I project one of them on the other, subtract that component from the second one, and I will get this remaining part which is perpendicular to the first one. Okay, this is very simple idea. This is what is actually studied by Schmidt and Gram, German mathematicians. So he is known as Gram-Schmidt orthogonalization. So I can do that and I can create this. Now this can be done not only for two vectors but for any vectors. So I can just keep on doing this, and this is the idea. If I have the original vector b1, b2, b3, bn, I can create b1 tilde, b2 tilde, bn tilde by doing some kind of a transformation. And the transformation is actually removing the components corresponding to that vector, corresponding to the previous vectors, and subtracting from the current one. And hence these mu2 1, mu3 1, mu n 1, etc. These will be some values which will be subtracted. Suitable values will be subtracted from the corresponding vectors. Okay. So this actually will work very easily, and this is a polynomial time algorithm. So given any basis vector, I can create another basis vector which is now in good shape. Earlier one was not orthogonal, new one is orthogonal, and this can be done very, very efficiently. Okay. The problem here is that if I do it for lattices, this one might be a basis for the lattice, but this transformed one might not be necessarily a basis for the lattice. They are orthogonal guaranteed, but this is not guaranteed that the now basis. Because we already saw in some examples that it is like this example here. I had this one was not a basis. They are orthogonal, but they are not covering all the vectors. So I can create from given vectors some orthogonal vectors, but this is not guaranteed that they will remain the basis. Okay. Now there is some new things that I want to cover, because this is related to crypto now. I'm slowly coming towards crypto. From math I am coming to crypto. So there is a problem which is known as find the shortest lattice vector, and this is known as the first minima of the lattice. So here is the lattice. This dot here is the center of the lattice. So origin 0 0. I can start anywhere because this is infinite lattice. I can start anywhere. Okay. So I have taken this as 0 0. Mostly we will have finite lattices, so there will be a specific point called 0 0. So I start from here, and now I slowly increase the radius of this ball till I hit upon one vector which is one point which is in the lattice. Whatever is that distance is called the first minima of the lattice. So that radius which covers the first point within lattice. The point need not be unique, but the distance will be unique, because the moment I hit any point, I will stop it. That is called first minimum. Okay. In this example, B2, the length of B2 is that first minimum. Okay. Because if I do anything less than B2, starting from here, I will not touch any point. I will remain in an empty area only. Okay. So, for example, if I have a lattice generated by the point 1 1 and the vector 1 1 and vector 2 0, then the first minima is square root 2. The shortest vector need not be unique, but the shortest length is unique. Okay. In general, why the shortest vector is not unique? If V is a vector which is shortest, then minus V is also going to be shortest, because the same length, but it is the other direction. V is here, minus V will be exactly opposite. Okay. So this shows that at least there are two vectors which are of same length. Now you can extend it and okay. So right now I'm talking about now norm. Norm. The first norm is simply the sum of all the coefficients, all the parameters, the modulus of them. So if I have a vector which is x1, x2, x3, then the absolute value of each of these components summed up is called the first norm, the L1 norm, and the maximum value among these absolute value is called the L infinity norm. L2 norm, standard norm, which is the length of the vector. Okay. The L2 norm is the Euclidean distance. Now there is something that we already know. I start on a lattice which is defined by a basis vector. I do Gram-Schmidt orthogonalization, and the only trouble is Gram-Schmidt orthogonalization. Nevertheless, I have created some set of vectors which are perpendicular. Now in those vectors, I look at the least value. Whatever is the smallest vector here is certainly giving me a lower bound on this lambda 1, the first minimum. So whatever is the minimum vector in my basis, whatever is the minimum length vector in the basis, it is of length at least the minimum vector in the Gram-Schmidt orthogonalization process. That is one result I have. Okay. And here is the example. I had this vector v1 and v2. I did v2's projection on v1, removed that component. I left with this green colored v2 tilde. Now v1 and v2 tilde are perpendicular. v2 tilde is the smaller one. So I am guaranteed that whatever is the lambda 1 for this best lattice, it is going to be of length bigger than v1, v2. because whatever is the smallest vector in this orthogonal vectors that I created, the least one is going to be the lower bound for lambda 1. So I have this thing. Then I have upper bound also on lambda 1. If I had a lattice L given by certain basis vectors, I can create the volume of the parallelepiped. Remember the parallelepiped I talked about a little while ago? So that parallelepiped here in this picture we have this parallelepiped, this one. So and this one. So parallelepiped is just this linear combination in the entire area, okay, where the linear combinations are taken with real values between 0 to 1. So some value x times of b1 plus y times of b2, where x and y are between 0 to 1. So here also the same thing, x times of b1 plus y times of b2, where x and y are between 0 to 1. So that parallelepiped I create, the volume of the parallelepiped is called the determinant L. Okay. So determinant L's nth root multiplied by under root n is the maximum value of lambda 1. So I have actually both the lower and the upper bound on lambda 1, but there is a big gap. Lambda 1 is certainly less than this value, lambda 1 is certainly greater than the Gram-Schmidt smallest vector, okay, which can be computed in polynomial time. Okay. And this also we have some methods to compute the determinant of L, the volume of the parallelepiped. So we have some method of computing that. So I have an upper and a lower bound on lambda 1, the least, the smallest vector. Okay. Now you can actually extend this idea to successive minima. So how much should I extend so that I have now not one vector but maybe the next one also? So this is called lambda 2, lambda 3, lambda 4. In particular, lambda I is the smallest number k such that there exist I linearly dependent lattice special vectors. Now based on these, I have some computational problems on lattices. So there are three important problems which are actually, I am interested in these problems because these are hard even for quantum computers. Okay. So this is what brings us to cryptography. So lattice was necessary to be explained because otherwise I couldn't even explain the problem. Okay. So the first problem is called SVP, the shortest vector problem. The second one is called CVP, the closest vector problem. And the third one is called SIVP, shortest independent vector problem. So these are the three problems, and using them we are going to create cryptographic algorithms. So what is SVP? SVP can be in two different settings. Like in computer science, theoretical computer science, you have lots of problems which are computational and decisional. Okay. Like computational problems are compute this value. Decisional is tell whether this is greater than this or less than this. And so there are this computational version which is called search SVP. I give you a lattice, which means I have given you basis vectors, and I ask you find the shortest vector in this lattice, which is such a vector u whose length is lambda 1. Okay, lambda 1 is that least length. So you have to find u such that its length is equal to lambda 1, the least length. So this is why it is called shortest vector problem. It is the shortest vector in that lattice. The decision version of it is that I give you a real number d, and you have to tell me whether that d is less than lambda or more than lambda. So you cannot even know that lambda 1. Computing lambda 1 is a very hard problem. Despite me knowing an upper and lower bound, the range is large. Between this range, what is the actual value of lambda 1, even when you are given the basis, is a hard problem. Even quantum computers cannot solve it. So even quantum computers cannot solve it today. I mean forever. No quantum computer can solve it in polynomial time. Okay. So the search problem was you have to find that vector whose length is lambda 1. In the decision version, I give you a d distance. You have to simply tell me whether this distance d is more than the lambda 1 or less than lambda 1. Okay. Whether lambda 1 is less than d or lambda 1 is greater than d. You can't even distinguish between the two, which means you have no idea about lambda 1. Okay. This problem is extremely hard. Decisional SVP. Then there are approximate versions of the same problem. So in the morning somebody was asking me about approximate problems, so here is the approximate algorithm. Okay. So we're talking about approximate version. In an approximate version, I don't even care about lambda 1 now. I say, okay, there is some parameter gamma. Okay. So can you find out a lattice vector whose length need not be equal to lambda 1, but it is whose length is less than gamma times lambda 1. So gamma is that approximation. Maybe gamma equal to 3. So I'm not even trying to find out the least vector. I'm trying to find out a vector whose length is at most 3 times the least. Can you find out such? So that is the lambda 1. Okay, this u. The length of u is at most gamma times lambda 1. Even this problem is hard. And then the parameter is gamma. So SVP gamma. Not all values of gamma make this a hard problem, but there is a range of gamma for which this problem is hard. Okay. Then there is a gap SVP problem. So again, just a search version. Now we are making a decision version of this search problem. Now I will give you a number d. You have to tell me whether the least vector length lambda 1 is it less than d, or it is gamma times, or it is bigger than gamma times of d. So I am giving you a d. You have to just figure out whether it is in one small circle or outside some circle. In between there is a gap which I am allowing. In the previous one I was not allowing this gap. I was simply asking you whether it is less than d or more than d. Here I am saying, is it less than d or more than 3 times d? In between I am not even telling you. I am telling you that the answer is either here or there. Can you tell me where? Okay. You cannot even tell me this. Okay. So this is the gap problem in this shortest vector problem. All these problems are extremely hard for quantum computers. Then there is the second problem called CVP. Okay. And this is closest vector problem. The first one was shortest vector. Now we are talking about closest vector. So closest means related to something. So I have one vector and I will try to find out a vector which is close to it. Okay. So we are talking about lattice points, remember. So I am giving you one lattice point. I am telling you, can you find out another lattice point whose distance from this point is the shortest among all possible lattice points. So that is called closest vector problem, CVP. So I am giving you this basis. I am giving you T, and you have to find me a vector u which is on the lattice, such that u minus t is lambda n, which there are not more than this n points in this circle that you create. If I create a radius t on u, I will not have more than n points. Okay. And then there is a decision version of it. So I give you a t which is any random point. Okay. So here also I am giving you t is a random. So remember, t is in Zn. It is not on lattice. U is on lattice, remember. So I give you some point in picture. So like look at the picture again, maybe to make it simple, what I mean. So this is the lattice. Okay. I am giving you a random point. That random point could be even here, for example. It could be here. Okay. It need not be on lattice. You have to find out the vector which is closest to this and on the lattice. So if I give you a point here, your answer should be this. Okay. So if I give you a point here, your answer should be that. Okay. So you have to, I give you a t, you have to find a z which is on the lattice and closest to it.
So nearby 2 points are there?
So any one of them. In general, I am talking about n dimension. The moment you talk about higher dimension, it is actually a very sparse area.
That could be a different answer on that time.
No, the distance will be the shortest. So which if there are 2 points which are equally close, give answer any one of them.
But it can be another answer for another point.
Of course, in some cases it can be. No, that shortest vector need not be unique. The length is unique. So look at this. What is the definition of shortest vector, the closest vector problem? So I give you a t which is just a random point in Zn. Okay. U is on the lattice. So you are given t and you are given the basis vector b. You have to find out a u such that u minus b t, which is the distance between this lattice point and t, it is lambda n. So if I give you n equals to 1, that means it is it is less than the lambda 1 distance, which is the shortest vector. So you are not going to go beyond the shortest vector from that point. So if from t I make a circle, I will get only one point, which will be this u.
Like that, earlier the point is coming between the lattice. Like it will be.
No, so there will be only one point which is going to be closest to t and on the lattice.
In figure 3 you are showing that the point is between the lattice.
No, so here for example, here in this picture, so I give you any random point. So if I give you this point itself, then this is your answer. Okay. But if I give you a point here, what is the closest point to this? So I know this is the lambda 1. Okay. So from this point I make a circle of lambda 1, okay, radius lambda 1. Whatever point comes here will be the closest point. So that is what we are trying to talk about in this example. Okay. So we are talking about the closest point which is on the lattice. Okay. So even when I am picking a random point and I am giving to you, you can't even find the closest point. This is a very hard problem. Okay. So this is the closest vector problem. Okay. And then there is a decision version. So if I give you a t and a number d, you tell me whether there is, if from t you create a radius of d, whether there is a lattice point inside or outside. You can't even distinguish. Okay. So this is, I give you a number d and I give you a point t which is random point. Okay, need not be on lattice. So from t, I look at the nearest lattice point. The distance between them, is it less than t or more than t? You can't even distinguish that. So forget about finding the shortest. You can't even find out if this distance is enough or not. These are all very hard problems. And then there are approximate versions of the same. So now I will have simply a gamma also. Just like previously I had gamma here in the SVP and decisional SVP's gamma versions. Okay. Search SVP gamma, decision SVP gamma. Here also I will have CVP and decision CVP, and there will be gamma versions of the two. Okay. And all are very hard. SVP is actually proven to be NP hard, shortest vector problem. Okay. And not only hard, even an approximate solution is hard. So I can't even approximate to a constant number. I can't even find 2 approximation, 5 approximation, 10 approximation. Okay. So, but SVP with gap, that gamma thing, if I take gamma to be very large, under root n, then it is unlikely to be NP-hard. We don't have a proof yet, but it is believed that it may not be very hard. So what we can do is, I have to take this gamma to be actually at least n. If I take gamma to be n, then I can create a hard problem which is not solvable as of today. And some of these problems actually were solved was using LLL. That's why I mentioned LLL earlier, Lenstra-Lova's algorithm. This was used to actually solve SVP for certain values of gamma. So if you look at it, for certain values of gamma, LLL can solve. Okay. For values of gamma below this, these problems are hard and they are useful for crypto. Below this, these problems are in NP and intersection of co-NP. These are believed to be NP hard. These are not believed to be NP hard, sorry. So these might be solvable, okay, and these are NP hard. Okay. So this intermediate area is of use. So n and up to some 2 to the power n log n over log n, up to this gamma, they are useful for cryptography. So I'll skip all of these things. So I want to talk about, I don't want to talk about LLL. I want to talk about this lattice-based crypto. So in lattice-based crypto, I have this problem known as short integer solution problem. It can be shown to be connected to this SVP, CVP, etc. There is a reduction between them. So if I can solve this, I can solve that. So these are called reduction problems. Okay. So which is the easiest reduction I can give? Maybe I can give any example of reduction. Okay, so there is a joke that I can tell. Okay, so it's too much for mathematics, so maybe a joke will be nice. So a mathematician is asked, a physicist is asked, how do you prepare tea? And he said, I will take a water kettle, I'll fill it with water, I will put some tea leaves in it, then I will switch on the gas and I will put it on the burner. Once the water is hot, then I will pour it and maybe if milk is required, then I will add it. So done. Okay. So he said, I will boil the water and done. Now a mathematician is asked the same problem, but he is given a different problem. So mathematician is said, you have a tea kettle already full with water. You have a gas which is already burning. How do you prepare tea? A mathematician says, I will switch off the gas. I will throw away the water. This reduces the problem to what we have already solved. So this is a joke, and this essentially tells you what is reduction proof. So when you want to solve a problem, you transform the problem into something which you already know how to solve. Okay. So these are known as reduction proofs in computer science. Okay. So there is a reduction proof between SIS and CVP. So if you can solve SIS, you convert the SIS problem into a form of CVP problem. And then you say, if you can solve this, then certainly you can solve that, because this problem actually transforms to that. But we already know that problem is hard, hence you cannot solve this. Okay. So this reduction proof actually tells you impossibility. Okay. That is how reduction proofs are very, very useful, and lots of reduction proofs are there in cryptography, in particular in lattices. Okay. So what is the SIS problem? So SIS problem says that I'll give you a matrix A from ZQ. Okay. So matrix is of size n by n, where n is small, m is large. So it's a short, fat matrix. Okay. So number of rows is less, number of columns is large. So it's a short, fat matrix. Okay. N is much, much less than m. Then what I will do, I will take elements of this matrix. There are n times m elements which I need to fill. These elements will be filled from ZQ. ZQ means where q is a prime number. So I will take numbers between 0 to q minus 1. Okay. So mod q elements are being taken. So this matrix A belongs to ZQ over n by m. That essentially means the size of the matrix is n by m. The elements are coming from ZQ, which means all elements are between 0 to q minus 1. Then I will take a number x, which is non-zero. I am not allowed to take simply 0, 0, 0, non-zero vector. But the values are coming from minus beta to plus beta. Okay. And then I will multiply A times x. And my goal is to find such an x such that A times x is 0 mod q. So because I am working modulo q, I want all answers to be modulo q only. So I want 0 mod q. Okay. So this is the problem I have. Ax equals to 0 mod q. Okay. Now not only that, I mean you first forget this condition. I give you a matrix A of size n by m, where all entries are between 0 to q minus 1. And I give you this equation Ax equals to 0 mod q. Can you solve this? Okay. Forget about this x condition. Okay. You have a matrix A, you have to find those vectors x such that Ax equals to 0 mod q. These vectors are called in the null space of A. Okay. This is the definition in linear algebra, null space of A. And this is very easy to solve actually. You have already done in school Gaussian elimination. So this Gaussian elimination you can implement. It will take order n cube time, where n is the size of the matrix. Here n by m, so n rows actually, so n equations actually in m variables. You will be able to solve it. The problem comes because I am now saying all solutions I don't want, because everything is mod q. Okay. So you have many solutions actually. So what I want is solutions which are bounded in size. So every value should not be very large. Beta will be a small number. Maybe say I can even make beta to be 1. So your answer should be either minus 1, 0 or 1. Every value in the vector x should be either minus 1, 0 or 1. Can you find such a vector which will give you Ax equals to 0 mod q? So I am limiting the size of the norm of the vector x, the Euclidean length of the vector x. And that is why it is called short integer solution. So it's a solution to Ax equals 0. This is the equation. But you have to find a short solution. Short solution because I am putting some restriction on the length of x. Okay. And this problem is extremely hard. Okay. Short vectors satisfying this equation are known to be extremely hard. Not only that, now what I will try to do is, I am actually defining it. I give you a matrix A. You have this script A, or this math cal A, okay, calligraphic A. This is an algorithm. So this is an algorithm that you are running. This is your input. Algorithm's input is the matrix A. The probability that your algorithm outputs x such that Ax equals to 0 mod q, and the length of x, the infinity norm of x is beta. What is the infinity norm? The maximum value inside this vector x. So infinity norm is beta, which means the values that you have in that vector x, the largest value is beta. And it is magnitude. That tells you that the values are actually between minus beta to plus beta. That's all we are saying. And this problem, if you try to solve, the probability that you will find such an x is extremely small. So this probability is close to 0. It is 1 by 2 to the power n kind of a probability. Okay. This problem is known as SIS problem. Short integer solution problem. This has connections to CVP. So this short integer problem is extremely hard. Then using this, actually I can create hash function. So I will skip this. I will not talk about this. I can even prove why a hash function can be created, and I can reduce it to the SIS problem. So I'll create a hash function. I'll show that this hash function is actually, if you can find conditions for this hash function, that means you can solve the SIS problem. So I'll skip that part. I want to talk about something else. There is some one interesting part which I want to talk. There is something called leftover hash lemma, whose main implication is this. You have a matrix A, and I define a function H, which takes two inputs A and X. A is a matrix, X is a column vector, and the function H applies A times Q mod A times X mod Q. So this matrix is multiplied by a column vector. You take all operations mod Q and create a column vector. Okay. So this is the function H, which takes two inputs, the matrix and a column vector, produces a column vector. Okay. Now, if I give you A and I give you the hash, this function H with AX, but I don't tell you X, and I give you a different answer now. I give you the matrix A and I give you a random vector Y. Then these two are statistically indistinguishable. Which means if I give you a matrix A and a random column vector Y, you can't even find out if this Y was obtained by multiplying some X by A.
The two A are different.
No, this is the same A. This A and this A is same. So despite you knowing A, since you don't know X, you cannot even figure out that if I randomly picked a Y, or this Y is actually coming after some X being multiplied by A. That X you don't know. If you knew, then you would have multiplied and checked. Okay. So I am giving you a random vector Y. So this AY looks like as if it is coming from A times X. Okay. So these two are statistically indistinguishable. Or in other words, A and A dot X are looking like A and Y. Okay. This is the leftover hash lemma. Okay. And actually this was used by AICTE in 1996 to prove something, and this actually leads to Regev's work. Regev did something which is known as LWE problem, learning with error problem, okay, LWE. And for this paper, he was given Gödel Prize in 2018. It is like a Nobel Prize of Computer Science. Okay, so he received Gödel Prize for this paper, where he introduced the LWE problem, learning with error. Suppose I give you a problem AS equals to B mod Q. S is unknown. Okay, A is a matrix, B is a column vector, and you have to find a vector S such that A times S equals to B. Okay. Can you solve this? Very easily. You have been doing this in school, isn't it? AX equal to Y. You can find X by Gaussian elimination. Okay. In school, all of us have done this. Actually, we are taught it by hand, but that is actually Gaussian elimination. In 10th class itself, we are taught this, isn't it? So that is precisely the problem. Okay. But now we modify the problem a little bit. I will not give you this exact equation AS equal to this. S is used for secret. So S is not given to you. S you have to find. So I give you A and I give you B. And of course Q is known to you because that is the field in which we are working. So mod Q. So I ask you, can you find the secret S such that AS equal to B? Surely you can find. But now I will introduce error in the problem. Okay. So what is the error? So I will take noisy equations, not the real equations. So rather than taking AS, what is the first value here? So I have a matrix A and I am multiplying by a column vector S. Okay. So how does the multiplication happen? Is it pen here somewhere? Pen है क्या? ये marker है? कहीं marker है क्या? वहाँ पे यहाँ पे इसका marker है? नहीं लिखा है. So I could have actually written here. So makes it easy to understand. यहाँ दिख नहीं रहा है मेरे को. नीचे क्या थे? अच्छा मिल गया. तो सर को बुला लो. लोबियल सर आ जाइए वापस. मिल गया. हाँ चल रहा है. Okay, so this is the kind of a situation. Okay, matrix A multiplied by S equals to B. Okay. Now, how do you multiply? You multiply this by this and obtain this value. Okay. Then you multiply the second value, multiply by this, and you obtain this value. Okay. So essentially, all values in this B are obtained by this one row of A multiplied by this S vector. Okay. One row multiplied by S gives you one value of B. Now, what I am trying to do here is I am taking S every time, but these rows are changing. So I am taking first row is A1, second row is A2, third row is A3, and so on. So this row is A1, this row is A2, this row is A3, and so on. So what is the equation actually? A1 dot with S in dot product sense equals to, here I will call it B1. Then I have A2 dot S equals to B2. These are the equations actually I have.
Yes, sir.
Now what I am trying to do is I am adding one more error term E1 here. So now I have S times A1, that dot product, which is what I am writing, plus E1 equals to B1. So I introduce some error. That error is very small. So this E is typically in the range of say -1, 0 or +1. Sometimes it could even be 0. So I now give you these erroneous equations, noisy linear equations. And now I ask you to solve this. Suddenly this problem becomes exponentially hard even for quantum computers. A beautiful thing. Okay? Even quantum computers cannot solve it. Because for each equation there are three choices now. -1, 0 or 1 error. And there are n equations. So you have 3 to the power n equations to solve. Okay? And you cannot figure out which is the best solution. So suddenly this problem becomes extremely hard, and this is precisely what is the learning with error problem. So just simple equations but with error, and suddenly this problem is extremely hard. So what LW says, I will give you A and I will give you that vector B, but that B is not coming by just A times S. It is coming A times S plus some error vector. Can you find out what is that secret S? And you cannot find out. So this is learning with error. Okay. So this in equation form, if you write, it is not just A times of the vector S, but also there is an error vector E, and now this is equal to B. So this is the equation. AS plus E equals to B, where E, every component of E is very small. Either -1, +1 or 0. Or you can actually make E to be anything between -q, +q, something. So you can choose some value of E. Even for the smallest possible -1, +1, 0, this problem is not to be hard. There are even this distribution. So if I look at the distribution, so I can actually take S times of A plus E. This actually looks like a random value. So whether I am giving you A and B independently, or I am giving you B as S times of A plus E, you cannot even figure out. So what it says here is this: I give you A, and I give you A times S plus E, which is the vector B. So you have these two inputs. Your adversary A is allowed to run in polynomial time in n. Can you figure out what is S? The probability for this to happen is extremely close to 0. Very, very close to 0. So this problem is called extremely hard problem to solve. And there are again this decisional version also. So you cannot even figure out if I give you A and I give you a B like this, or I give you a random vector in place of B. You cannot even figure out which one has been obtained by this AS plus error equal to B, or whether this B is completely random. And using this, there is a connection to lattice, which I am skipping because of time. And I want to actually talk about encryption directly. So there is a Regeus encryption using this LWE problem. What he did is this. This is a paper published in Stock 2005. What it says is that I take a random matrix of size m by n. This is the matrix A. I create an error vector of length m. But this is not just a random vector, it is a vector created by Gaussian distribution. Because the proof requires Gaussian distribution. So it took a random distribution based on Gaussian, a normal distribution. Then he chooses a secret vector S of length n. So this is S of length n, where every entry is coming from ZQ, which means between 0 to q minus 1. Every entry is 0 to q minus 1, 0 to q minus 1, and there are n such entries. Then you compute this value B, which is S times A plus E. E is the error vector, A is your matrix, S is your secret. So it is precisely what we did here. We are computing this. Now you publicly publish A and B and keep the secret with you. Don't tell secret to anybody. This is your public key setting. Remember what is public key cryptography? You have a public parameter and you have a secret parameter. You are the person who is setting up the system. So you create your public key and put it on your website. Anybody who wants to encrypt a message for you will choose these public parameters and encrypt a message. And only you will be able to decrypt it using the secret that you have. Others will not be able to do it. That is public key encryption. So that is the point I want to explain using LWE now. Okay. So what is this thing? We created a random matrix. Remember, this is dollar means random. So a matrix A has been created by dollar, which means uniformly at random, of size m by n. Every entry of the matrix is coming from ZQ, between 0 to q minus 1. A vector E of length m is coming from this chi, which is normal distribution. Secret S is being chosen uniformly at random of length n, each entry coming from ZQ again, 0 to q minus 1. Then you compute a vector B. So because it is hard to write a column, so I have written B transpose. Okay. So B transpose, that's why I am writing S transpose A rather than writing A times S. Okay. Because I don't want to write a column and fill the entire page. In one line I can write if I write transpose. Okay. Because now it's become a row vector. Okay. So B is nothing but A times S plus E. Essentially it's just a way of writing. A times secret, A is public, S is secret, plus B, plus error. So that error is also not known to people. Then you publish A and B and keep the secret S. Because of the previous result that I showed you here, previously here, somewhere here, here I was showing you. Okay. So this vector B looks like a random vector. You cannot even figure out if it is random or it is coming from this computation, A, S plus E. So what you are giving to people for public key, you are giving a matrix A which has been actually computed randomly, and the vector B which is also seems like randomly computed. It is not randomly computed but looks like randomly computed. People cannot distinguish it from a uniformly random vector B. So what you are giving as public parameters is something random value. What is the real thing from where you computed B? That is S, that you are hiding to yourself. Now if somebody wants to encrypt a message, the message is now encrypted like this. You will sample a short vector R of length m. So you are simply taking a m bit string 0 1 0 1 0 1. This vector R you took. Then you compute A times R. A is public, everybody knows. So you want to send a message to me. I know secret S, but I have not told you. I have told you A and B only. You are interested in sending a message to me. So you are going to compute, you are going to pick any random R and you are going to compute A times R. Okay. Matrix is with you. R is yourself chosen, so you can multiply and get a vector U. Okay. Then what you are going to do, you had that vector B, which is also public key, the second part of the public key. Public key was A and B. So that second part B you will take, you will multiply it by R, and then you will multiply it by Q times, mu times Q by 2. Now mu is an interesting thing. Mu is either 0 or 1. Okay. Again you will pick this, either 0 or 1. Randomly you will pick mu. Okay. And what is this Q by 2 doing? So Q by 2 is going to round it to the nearest integer. So you are just taking that number Q and dividing by 2. So if it is mu is 0, that means you are not adding anything to V. If mu is 1, then you are adding roughly Q by 2. Okay. And then you output your cipher text as U and V. Now anybody who looks at U and V will think that U is random because A was random, R is random, so U is random. So U is completely random. V now has B multiplied by R, so this part is random. Mu also is something that you have chosen, and Q by 2 is one of the two values. This thing will look like random to somebody who receives it. But the decryptor will be able to decrypt it using the secret S that you know. How? So the decryptor will actually be able to decrypt this. Mu is your message, by the way. Okay, I should have said. It can only encrypt 1-bit message. Okay. If I have 10-bit message, I have to repeat the same process 10 times. So it's very inefficient. And this is what Michiancio and other people did later. They made this an extremely efficient technique. So the first algorithm which was created is by this Regge. This is very inefficient. At a time, it can only encrypt 1-bit mu. Now, how is the decryption happens? So you are going to do some computation. At that, if that computation comes out to be some small value, then you answer 0. If the value comes out to be large, you will answer 1. Now, why does that work? So look at this picture. What is this you are doing? So you are going to compute V minus S times U. What is V minus S times of U? V, if you look at previous slide here, V was the second part, ciphertext. V was equal to V times R plus mu times Q by 2. So I am simply going to replace this V as this. So V is V times R plus mu times Q by 2. Okay. I simply copied whatever this U comma V you received. Okay, this is the ciphertext you received. Second part you took and wrote it here. Minus S times of U. Now what was U? Look at what was U here. U was A times of R. So when you are doing this S times of U, it is S times of A times of R. But now B was not random. B was computed very carefully. B was computed very carefully like this. So B was S times A plus E. So I will replace that here. B as S times of A plus E plus R multiplied by R plus this minus this. Now notice that S transpose AR is here as well as in minus here. So they will cancel out. What will you be left with? You will be left with E times R plus mu times. E times of R is an error vector term. R was randomly selected, but E is very small. That is the trick here. E is small, so error is very small. What is this value now? If I look at all values between 0 to Q minus 1, so 0 is here, 1 is here, 2 is here, 3 is here, Q by 2 is here, and Q minus 1 is here. Okay, so mod Q I am looking at a circle. Either I am adding this or I am adding this. If mu is 0, I am adding this. If mu is 1, I am adding this. Error is something little bit. So if I make guaranteed that error is very small, then either it will be somewhere in this range or I will be somewhere in this range, because error is very small. And hence, if I am somewhere close to 0, I will answer 0. If I am somewhere close to Q by 2, I will answer that the encrypted bit was 1. So this is precisely the trick. And what we show actually, that the bound can be shown to be about Q by 4. If the bound is more than Q by 4, then it will be trouble. Suppose the error becomes more Q by 2. Then the point was here, but the error actually brought it to Q by 2. To say Q by 4, the error went here. Okay. Now the answer may have been here, but if the error was Q by 4, then I could have been here. So when I am here, I don't even know whether I should decrypt to 0 or I should decrypt to 1. Hence, what I say is that the error should be strictly less than Q by 4. So if I can make the error small, then I will be actually falling either in this range or in this range on that circle, mod Q. So if I am close to 0, then I will say my bit was encrypted was 0. If I am close to 1, I will say my bit encrypted. If I am close to Q by 2, I will say my bit encrypted was 1. So 1 bit encryption can be done in this manner. And then we can show that this actually is in such that when I encrypt a bit 0 or when I encrypt a bit 1, the ciphertext for both of them looks identical. And computationally, the encryption of 0 with the same public key and the encryption of 1 with the same public key, they will look identical in distribution. So there is no difference to somebody who is looking at the encryption of 0 or encryption of 1. They will find similar distribution. Okay. So that is the proof of security of this encryption. Okay. Then there are some digital signatures which I am not discussing much because of lack of time. Then there are code-based crypto. In code-based crypto, there is an error correcting code. Based on that, you can create a cryptographic algorithm. What is currently there is in classic Michaelis. It's a very old problem, almost as old as RSA. But the only trouble is that key size is very large, so people are not using it. This is then there is Macaulay crypto system, which I have given here in detail. It is related to coding theory. So if you have done any course on coding theory, then you should be able to understand it much easily. Otherwise, you'll have to at least know about syndrome decoding problem. Okay. So it is related to syndrome decoding problem, which is known to be NP hard. Okay. So even quantum computers cannot solve syndrome decoding problem. So from there, this problem is coming. Okay. Then there is multivariate polynomial based cryptography, which is a digital signature scheme known as Rainbow. This has also been standardized by NIST, which I didn't even discuss. I knew that I will not have time. I was already on slide number 127 by this time. I was making these slides in the night. I didn't sleep all night last night, okay, to make these slides. Okay. So I stopped at this point, and then there is a hash-based crypto. I also didn't make any slides for this. There are schemes like XMSS and Sphinx, which are based on hash. So I did not make them. And the final one is isogeny. There is Psych, but Psych is already broken. So there is no scheme which is currently known about isogeny. Okay. And the summary is that there is a multi-year competition which is going on. There are candidates based on lattice code, multivariate and hash-based. There are research questions like optimizing now. Right now, you cannot create a new algorithm. That's extremely hard. Algorithms are already made. Now the question is, can you efficiently implement them? That is a very hard problem. So, in fact, MIT is giving projects on this right now on efficient implementation. And not only that, how can you transform from current schemes to this? So, can you create a browser where the encryption is not happening by the current handshake protocols, but by these post-quantum protocols, post-quantum secret protocols? So, in my browser, I simply want to switch from RSA to lattice crypto. Can I do? So, those kind of projects also MIT is giving. Then there are hardware implementation things, because these algorithms are slightly slower than RSA and DFLMA. So, we want to make it very fast. So, you can make a hardware software co-processor. So, there are a lot of papers of that type. Then the moment you have anything in hardware, there are side channel attacks. So, can you prevent side channel attacks? So, that is another problem. So, those are the kind of things people are doing. And the new standard into existing protocol, that is, as I mentioned already, in browsers and other things, this is a pending problem. Okay. This is where I would like to stop. Thank you very much. The slides are here, so you can take the slides. And if you have any questions, feel free to ask me. Okay. My email ID is just my name @iitjodhpur.ac.in. So iitj.ac.in. Okay. You will find it easily online. As you already understand, it requires heavy mathematics if you want to do anything. You need to understand reasonable linear algebra, a little bit of abstract algebra also. Okay. Maths is extremely beautiful.
Questions?
I understand it was very dense, very heavy math, but